Welcome, everyone, to this JMP academic webinar, Survival Analysis in Biostatistics, which will be presented by JMP Academic Ambassador Kevin Pochner. I'm fellow JMP Academic Ambassador Ross Matusalem. I'm just here to host today and field questions in the Q&A, while Kevin gives us a tutorial on survival analysis techniques, specifically with a focus on the methods most common in biostatistics, so things like Kaplan-Meier analysis and proportional hazards models. And if you're familiar with our webinar series, you may have attended teaching-focused webinars in the past where we assume you know the statistical techniques that we're talking about, and we're really helping you as an instructor of those techniques learn how to use JMP most effectively with your students. This, being the first webinar in our summer series, is really aimed more at upskilling folks with a focus on academic research. So this webinar is particularly appropriate for you if you know that you need to use survival analysis techniques, but need a primer on the basic statistical concepts and also how survival analysis techniques are implemented in the JMP Student Edition. So before we get started, I want to direct you all to Zoom's Q&A panel. So there's the icon that you're looking for right there on my slide. We encourage you to ask questions throughout using Zoom's Q&A panel. Using that instead of the chat just helps us keep track of the questions that have been asked and in which order and which ones have already been answered, and also allows us to display those answers to you in a way that is a little easier to consume. Feel free to use the chat for general comments to us at JMP or to your fellow attendees, but please do put your questions in the Q&A. And so with that, I think we're ready to kick it off. Kevin, are you ready?
I am, and can you confirm you can see my screen?
Yeah, we can see it.
Okay, perfect. All right, well, welcome everybody. As Ross shared, this is going to be about techniques, survival analysis methods in biostat. Oh, hold on, I got something on my screen. Just want to fix that. Okay. So part of the journal, and you'll get a link in the next day or two to the recording of today's session, as well as this journal file that you see open on the screen. And I always like to put some links to our resources. I'm not going to open any of them now for the preservation of time, but in here we have links to a lot of our teaching learning resources, like our videos and instructional guides, the academic webinar library, which is where this is going to go, our case studies and enhanced data sets, which you can use for demonstration in your courses or for student assignments. They're also great for actually learning methods too. They're not just for the classroom. There's a link there to some books, biostat books that feature JMP. Some of them are made by us. So they're kind of a hybrid of manuals and textbooks. There's also some traditional textbooks up there that feature JMP. I also have some links to help documentation on the methods that I'm going to show today. I also decided to add a link to a page that lists out all of the capabilities of JMP and JMP Pro. So if you kind of want to get an overview of the tools that we have, not just statistical methods, it's got everything from data management, importing data, as well as statistical methods, but that might be nice to go to. So if you're wondering if JMP can do something. And I also found this cute little article in the Smithsonian Magazine about John Grant, who I guess he's considered the kind of the grandfather of survival analysis. Back in the 1600s, he was creating some life tables for citizens of London. I guess it was kind of another wave of the plague was coming through. And so he's kind of considered the grandfather of survival analysis, kind of the most detailed documentation of survival rates. I think it goes back. I think the ancient Rome was doing it too, but not at the level that is. It's very, very brief. It's like about a 1-page, 2-page article, but I don't know, just something cute, or maybe you wanted to share with your students. But I'll let you guys go to those on your own time. For those who work with survival data, you're going to know what I'm about to share with you, but for those that are new, it's kind of important. What I think makes survival analysis unique is that the methods I'm going to show can handle sensor data. So when you're studying the time to an event, whatever that event is, you're going to have either the data as you have the exact value of the time to event, or close enough to the exact value, I should say. We call that complete data. So if there was a patient under study and let's say they survived 7.3 years, well, you would have that number 7.3. But what comes up a lot in survival analysis is censoring. And so one type of censoring, and probably the most common in survival analysis, is right censoring. And so that's where it's time, you can think of it as it's time to do the analysis. And one of the subjects in the study, let's say they are still alive. And so maybe they've been in the study for 10 years or 5 years or 15 years, but they're still alive. And so you don't certainly want to treat their lifetime as that number because they haven't died yet. All you know is that number you have is a lower bound. They'll eventually die at some point, but it hasn't happened yet. Or sometimes people just drop out of the study on their own accord. And so you don't know what's going to happen to them later. You just have them up to a certain point. Another type of censoring, it doesn't occur as much, but it's left censoring. And so that's where you have an upper bound. So you have a time value, but that's the most the number could be. So you can think of it as you don't know the start time, or something like, let's say you were testing for like a sort of a medical condition, and maybe you observe someone and you're like, well, geez, it happened at some point in the past. I just don't know when, but this is the first time I've observed it because of some test that was done. You can almost think of it like testing for having a virus or something. Well, and another type of censoring, which is actually the same as left censoring, is interval censoring. Because left censoring, the bottom lower bound is 0. But in interval censoring, you can have something other than 0 as the lower bound. So think about, having a patient visit every year or every 2 years or every 3 years. And the last time they were observed, they didn't have some condition you were looking for, and now they do. And you just know it happened between some 2 points in time. So you've got kind of a lower bound and an upper bound. And again, left censoring is basically that, right? The lower bound is 0. I used to have a professor that said, well, everything is interval censoring because obviously somebody's not going to live for 500 years. So there is some like knowledge you can say, well, the most it could be is some number. So I used to have this professor who used to think of it as everything is interval censoring. Okay, so I'm going to go through a couple examples. I'm going to start off by analyzing a single variable, so kind of a univariate analysis. And so let me open that file up. Okay, so this data set is, it's not necessarily important what it is, but basically it's measuring the time it takes particular athletes to recover from a muscle injury they have. And the data happens to be in weeks. So for example, this first subject, it was 26 weeks before they were back to full strength after the injury. Now, if you look at this data, this is an example of complete data. So I'm going to start off with this one. So in this case, we actually have the weeks to recover for everybody. There's nothing censored. We have that complete information. And I'm going to do 2 different analyses with this data. The first one I'm going to do is the Kaplan-Meier, which is sort of a non-parametric way to just sort of describe the recovery rates of these athletes. And then the second thing I'm going to do is I'm going to fit a probability distribution to the data. I'm going to use a log normal distribution, but I can fit others. So I'm going to start off with the non-parametric method, Kaplan-Meier. This is very, very popular method in survival analysis. I can't remember. I think it was invented in maybe the 50s or somewhere around there, but you see it very commonly used. So the way you access that is under Analyze. We have our reliability and survival menu. And I'm going to go down here to survival. Now, the time to event variable is this time to recover. I don't have censoring, so I'm not going to put anything there. Now, I'm going to click this failure, and I'm going to explain why I'm going to do this. So you'll see either the graphs, you can think of it as survival failure. So I'm going to hit OK. But in this example, the variable we're measuring is time to recover, not time to die. So lower numbers in this case are a good thing, not a bad thing. And so just so keep that in mind. So there's the time to event could be something good, something bad, and in this case it's something good. So the way the analysis is going to start off is I'm basically seeing a graph, a nonparametric step function of the proportion of people that are recovering at different points in time, different weeks in this case. And down at the bottom is shown those numeric values. And I think one of the reasons why Kaplan-Meier is so popular, especially in intro biostat courses, is you don't have to have a lot of statistical knowledge to do this. I mean, you're basically just counting, right? There's a certain number of people, in this case, that haven't recovered yet at a point in time. And then you go the next interval in time, and then there's going to be a count of a number of people who have recovered. And then at the next point in time, you're like, okay, well, how many people are left? These are people who could recover in the next interval of time, and so on. And so you're just kind of counting these up and tracking those proportions. And then there's some summary statistics, like, I've got the mean here. I've got some numbers of when, say, 25% or 75% have recovered. I can also add some confidence intervals to this. So here I can add point-wise confidence intervals. So those are 95% confidence for every point there for every interval in time. I can also add simultaneous confidence intervals. So that's trying to get 95% confidence across the whole range of weeks here. So that's why that one's going to be wider. If you want to oh, hold on, I want to see one more thing that I was looking for. No, I'll pass on that. Never mind. Now, remember, we're doing time to recover. So there's going to be a default set of names here, like survival and failure. And this question kind of comes up with me a lot with faculty, where they'll say, oh, I don't like the way the default names jump names, titles, and tables, etc. And in this case, it's particularly you don't like it because these are not failures. Well, every time you see anything, any text in JMP, well, you can just click on it. And so I can change this to recover. Same thing down here. It says 25% failures, but I could just say 25% recovered, for example. Or up here, I wouldn't call it a failure plot. I could say, oh, that's the Kaplan-Meier recovery graph. I'm just making something up here that works. Recovery plot with 95% confidence intervals. Same thing down here. I might want to say, well, that's not failure, that's recovered. And that would be not recovered, and so on and so on. So just wanting to let you know that you can go in here and edit any of this text you see in a report. And this is an example. You definitely want to edit it because they're not survival and failures. Now, if you're very brand new to JMP, when you want to save this to the data table, you just click on the top red triangle, go down the bottom, save script to data table. Let me move this right here. And you're going to see right here, you're going to see this report get saved. So you can give it a name. I'll just leave it as the default. And when I hit OK, you'll see that gets saved right there. So I can close it. And then if I want to see it again, I just click on the green triangle. One thing that's nice about this is, let's say you add more data. So let's say I've got athlete number 68, and it took them 20 weeks to recover. And then I have athlete 69, and it took them 24 weeks to recover. Or let's say I delete some. I'm also going to delete some information. Let's say I find out that, oh, well, these three athletes actually, that we shouldn't have included them in the data for some kind of reason. So I'm going to select them, go under the rows menu, and say hide and exclude. And you see that little symbol there. So that means when I run an analysis, it's not going to include those three. So now if I hit that same green triangle, run that survival analysis, it's now going to do the analysis on the modified data. So this isn't the same report results that I showed you previously. This is now based upon the modified data. Okay, let me turn those off. So I'm going to do something called clear row states, and those are gone. And then let me get rid of those two ones that I added. Now, the next platform I'm going to use is more general than that survival platform. This is one where I can fit different distributions that I think model the data. And so this is also, of course, in our reliability survival menu, and it's called life distribution. And so time to recover is the time to event. Again, I have no censoring. So I'm going to click OK. Now, here's the thing with this platform. It actually starts off with the nonparametric method, and you get to see the Kaplan-Meier estimate. So my preference is I like to use this platform over the survival platform because I can do the regular nonparametric Kaplan-Meier estimates, but I can also fit probability distributions to the data. And so over here on the left, I have some controls where I can say, so I'm going to turn off the intervals for nonparametric. So if I click on the log normal distribution, I'm getting the CDF, the cumulative distribution function of the log normal, and I can see it fit to the data. I can also change the scale. You know, a common method when you're evaluating distributions, when you make this probability plot, is you rescale the y-axis so that the cumulative distribution function for that distribution is a straight line. So you can do that. Sometimes I like to keep it in the original scale, but that's a common method. Now, if I'm going to compare distributions, I actually need to put it back there. So let's say I'm going to look at the y-bowl fit to that. And I'm kind of looking at these. And as you're looking, you can see that some of that there's more than one that are pretty decent fits to the data. But instead of sort of doing this manually to see what distribution is the best fit, you can actually choose to, I'm going to say, fit all non-negative distributions. And JMP is going to go through. It's going to fit a bunch of distributions here. And it's ranking these from the best fit to the least best fit. And you can see that the log normal distribution is the winner. It's using methods, the AIC and BIC methods of fit. But some of these other ones would be pretty decent to use too. But it is saying the log normal is the best fit to this data. I'm going to close some of this stuff up. And then what comes along with it, well, since I now have a function, a distribution, right, there's an equation that's modeling the data, well, now I've got some cool little interactive graphics that come out. And one of those things is our profiler. And so now over here on the left, I've got an interactive tool where I can choose a time to recover. And so I'll pick 25 weeks. And over here on the left, I have an estimate of the proportion of people that will have recovered by that time, along with the 95% confidence interval. If I wanted a different level of confidence, I can go up on the red triangle and say change confidence level, but the default is 95%. So this is really great because I think that's a lot more powerful and comprehensive of estimating something via this function than just looking at the Kaplan-Meier. So that's why if I can fit a distribution, I choose that over nonparametrics. That's my preference. If you, again, survival, nonparametrics, Kaplan-Meier, that's very, very popular and show a lot of publications, you know, they like that analysis and accept it. So I'm not trying to steer you entirely away from it. One of the other profilers that I like here is, so you can think of this as kind of the inverse of what I just did, is you choose a proportion, in this case, that's recovered by some amount, of, like in this case, let's say 50%. And then now I'm getting an estimate of the time, the number of weeks that that proportion will recover by, along with a confidence interval. Now, what I'm going to do is I'm actually just going to type in this number right there, 0.818871. So of course, the estimate of the time it's going to take to recover is going to be 25, because that's that. So basically, that 25 and that 25 and this is the same, and that 0.818871 is the same. The difference is which one is fixed, and then which one are you estimating? So are you estimating the proportion or the probability, or are you estimating the time to recover? And then that's where it's going to put the uncertainty, the confidence interval around it. And we also have the hazard function over here. Think of the hazard function if you're new to this. This is sort of like the rate or the instantaneous rate of recovery. Sometimes people think of it as a probability, but it's not, because in fact the hazard value can be greater than 1. So think of it as a rate. And where it makes the most sense is when you do comparisons and you look at the hazard rate for one time versus another and compare them. I'm going to do this in another example, and we'll look at comparing hazards shortly. Now, I also asked it to fit other distributions as I was doing it. So I've got all those same graphs and numeric tables of all those other distributions that I fit. But again, I chose the log normal because it was the best fit to the data. I'm going to close this guy. Now I'm just going to open up some examples of censoring. I'm going to go through this really quickly. I mostly just want to show the format that you need to have the data. So if you wanted to have run an analysis where you have some right censoring, this is how you organize the data. So you've got your time to event column. So in this case, it's just 10 subjects, and I'm measuring the years it takes them to pass. And you have to have this other column called censoring. And basically, I've set up a binary variable indicating where the censoring is. So I'm using the value 0 to mean complete data. So for those 3 subjects, I know the exact time that they passed. Here's another one, and then these last 2. And then the other 3 are censoring. So this first subject here, we studied them for 20 years, and that's the length of time we've studied them, and they're still alive. So all I know is that 20 is a lower bound, and so that 1 is the indication of that. This patient is 12.1 years, and it doesn't have to be long numbers. Sometimes it's short, like in this case, maybe this patient has only been part of the study for 1.5 years. Well, they're still alive, so we certainly want to include that. We want to say, hey, well, someone lasted at least 1.5 years. So sometimes the censoring actually are low numbers just by the nature of the study. So if you run an analysis, and I'll just use the life distribution. If you run it, you put your time to event variable there, and then you have to identify where the censoring is. And so I have this censoring column, which is I set it up as 0, 1. It doesn't have to be. You can actually use names and other things. And then over here this is where you're just telling JMP what value is indicating censoring. And then when you hit OK, I'm just going to go back to the log normal distribution just to show you that fit. So it is fitting a distribution based on the fact that I have 7 complete values and 3 censored values. And it's kind of using a maximum likelihood estimate. It's got like this likelihood function where it's got both the censored and uncensored informations coming back with estimates of the distribution and the parameters that fit it. So you don't necessarily have to know what's kind of going on behind the scenes. Just know that JMP is accounting for the censoring. And then you would do the analysis the exact same way I was doing the one with complete data. I can estimate proportions or estimate times. I'm going to open up a data set that's going to have interval censoring. And with interval censoring, you basically need 2 columns. So one column is the lower bound, and then one column is the upper bound. So in this case, subject 1, so they were fine at 6 years, and then say at 7 years when observed again, there was some medical condition. I don't know when it happened. All I know is it happened somewhere between 6 and 7 years. It could have been at 6.1 years. It could have been at 6.9 years. I don't know that. Same thing, here's another one, 11, 12, 15, 16. Now, I've seen a lot of people in practice, if it's always just the years that you're like, well, I'll just pick the midpoint, and there's nothing that wrong about that. But sometimes the interval is going to be much wider. And so, for example, here's a person that there is a gap of 4 years. So it happens somewhere in that 4-year interval. And here's one that happened in some 2-year interval. Here's 4-year interval, 3-year interval. And so when you launch the analysis platform, so whether you do life distribution or survival, you put in both of the columns, and JMP knows the first one is the lower bound and the next one is the upper bound. So it's taking care automatically that that censoring is happening. And I hit OK. And again, I have all those controls where I can pick a particular distribution to fit the data. Again, it's taking into account that I only have lower and upper bounds of the data. Or not of the, I've got some small lower and upper bounds and some large lower and upper bounds. It's taking all that into account. And again, I've got those controls like the distribution profiler and the quantile profiler. And then just the last one I'm going to open up is if you have a data set that has all types of censoring in it, it can handle that. So you don't just have to have only one type of censoring. So here's the data set where I've got some interval censoring here. So these first 10, that's all interval sensor data. This data I have here is right censored. Okay, so all I know is that these numbers here are the lower bound, and so you put missing values in the upper bound column. So all I know is it's at least 16 years, it's at least 10 years, it's at least 3 years. And then this one down here is left censoring, and so all I know that is these numbers are the upper bound. And so you can either leave this blank or you can put zeros there. JMP will know what to do. And again, it doesn't change how you run the analysis. Just put in the 2 columns. And I'm going to get the same kind of analysis. Again, I can choose to fit a distribution if I want, or I can choose to use the nonparametrics. And then so here's my Kaplan-Meier estimates. And then here, if I chose to fit a log normal distribution, then I've got my interactive profilers that I can use to estimate the time to the event or the proportion that will be where the event will occur by a certain time. Okay, so I saw a couple questions are popping up. I haven't looked at them yet, but I see them popping up. I don't know if Ross, you're answering them or we should look at them now.
I'm working on them right now, Kevin. I think you can keep going, and then if we take another break at some point, I'll let you know if there is anything else to address live.
Okay, perfect. All right. So the next thing I'm going to do is I'm going to shift to where we're making some comparisons. And so the first one I'm going to do is comparing some groups. Okay. So this is actually a continuation of that example where we're tracking the time it takes an athlete to fully recover from some muscle injury. So I've got those 67 observations where I have complete data, and we'll call that the standard method. And then there's a set of athletes. You see, we've got 10 athletes where we're going to give them a different treatment, and I'm just going to call it treatment A. That could just be about what the rehabilitation looks like. And then another treatment called treatment B. And those two have some censoring. So treatment A, you'll notice, has 2 censoring right there. So at 20 weeks, we stopped. In fact, in this case, all of the censoring is at 20 weeks. So you can think of it as like, okay, we want to run some analyses, and we're still waiting for those 6 athletes to recover, and they haven't yet, but we know it's going to be sometime after 20 weeks. Now, what I like to do is I like to graph the data. You just have to keep in mind that some of the data is censored. And the way I do that is I can highlight all of the censoring rows. And then if I go under the rows menu, I'm going to say markers, open circle. And then you see how in the row states there are these open circles. So now when I create any graph, those particular rows, those values of 20, I'm going to see a different symbol. So I'm going to start off with the standard kind of comparative dot plot graph. So I just opened up the graph builder. Those of you who are new to that, the graph builder is, now we have graphs everywhere in JMP, and so there's always visualizations. But if you're just kind of creating a graph not tied to a specific analysis, you're typically using the graph builder. It's a blank canvas waiting for you to make a graph. So you just drag variables into different places. So I'm going to put time to recover on the y-axis. And then I'm going to put treatments on the x-axis. And then now I've got a dot plot. And then notice there are my censored values. And so this is just to make sure I don't think those values are actually 20. See, there's some time after 20. So maybe this person's going to be 25. Maybe this person's going to be 27 and 22. And like, I don't know where exactly these are going to land. All that I know is they're somewhere above 20. Now, you certainly look at this and you'll notice that, well, the ones that recovered the fastest are from these new treatments A and B. I've got 3 from A and 1 from B over here. So there's kind of an indication that they're doing better than the standard. But it's just something you got to keep in mind, that censoring, because when these spread out, then, well, how does it compare to that distribution? So I'm just graphing the data. Just make sure you keep track of what is censored. And so I can do a couple of different things. I can do the Kaplan-Meier, which I'll do that first. And so I'm going to put time to recover. I have to tell it the censoring column, because remember, I've got those 6 observations censored. And here, treatment is my grouping variable. Now I'm going to do that same thing where I want to plot, because I want to plot sort of the recovery rate. So I want it kind of increasing. I know, again, that's not a failure. And I would go in here and change all these names. Instead of calling it failing, I would call it recovered. But now I'm getting the 3 Kaplan-Meier curves, as well as down here, the Kaplan-Meier estimates for each of the 3 groups, as well as the data combined. And so what's just happening here is the concept of censoring is taken into account. And there is a statistical test. 2 different tests are shown here. Testing if there's equality among the groups. And it turns out there's not. We have statistical evidence of a difference. Now I can add confidence intervals to that like I did before. And so you're probably getting an indication here that maybe A and B aren't different, but it looks like there's some difference to the standard. But to do a little bit more of a detailed analysis, the platform I'm going to launch instead is the proportional hazards. So I'm going to set this up the same way, time to recover, censoring there, make sure it knows value 1 is the censoring. Again, you could use names, it doesn't have to be 0 or 1. And here I just have this 1 factor treatment. I could have more than 1, and I'm actually going to do that after this. And I click run, and we have there's some tests in here where we're going to see that there is a statistical difference. I know we saw that in the Kaplan-Meier approach, but we're seeing it here in the proportional hazards as well. But what I want to go to, the main function, whoops. So again, here are some testing for equality. But what I want to do, and what you typically do here, is you display the hazard ratios. And so basically what's going on here is it's comparing what is the hazard rate between the groups. Now it's sort of a constant hazard rate, not to say it's the same interval, it's kind of multiplicative thing. I mean, basically what's happening here is if you looked at the formula for these, it would basically be E raised to a coefficient divided by E raised to another coefficient, and you're basically looking at those ratio of hazards. So what JMP is doing is there's 3 comparisons, right? We have comparing A and B, A to the standard and B to the standard. But what also is being done here is it just sort of plots the reciprocal or calculates the reciprocal as well. But it's the same. So you can see that the p-values that 0.1879 is the same as that one, and the other two are the same as those ones there. So now I can do comparisons. You can almost think I'm doing little multiple comparisons here. And so if I compare the standard to A, I have a significant difference. The standard to B, I do not. And A to B, I do not. So right now at this point, I've only got evidence that treatment A is better than the standard. And the way you interpret the hazard ratio is it's basically the instantaneous rate of recovery from one group to the other group. Now I'm going to pick these ones here just because I want I want to put the treatments on the numerator. And so the way I would interpret that right there is saying that the recovery rate for treatment A is basically 4 times that instantaneous recovery rate for the standard. Now I've got a confidence interval here, so if I wanted to be proper, I would say that that instantaneous recovery rate is somewhere between 1.8 to 8.9 times the size of the recovery rate for standard. So yeah, it's a wide interval, maybe wider than you'd like, but well, I got to deal with what I have, right? I've only got 10 observations and treatments A and B, so there's certainly uncertainty there. Now I'm going to continue this example by doing this in the life distribution platform. And so here is where, whoops. Okay, sorry, my mouse is getting a little funny here. Put my censoring in here. And so if I set it up this way using the by variable, then what's basically going to happen is it's going to run 2 separate analyses. And so I've got 3. I've got A, B, and standard, and then I can go in there and try different distributions. But in this approach, you're just running separate analyses. And so that by role exists in almost every platform in JMP. If instead I'm going to do this under compare groups. Now treatment is my groups, got my censoring, and so now it's going to combine the analyses. And so now, for example, I've got those distribution plots overlaid on each other. So here I can fit, in this case, the 3 log normal distributions. And then I've got those profilers down below for each. Now I'm going to continue this example, and now I'm going to bring in another variable. Oops, open the wrong one, sorry. So now it turns out that I was sort of combining all these injuries when there's actually different levels of the injury. And so I'm going to incorporate this other variable, this numeric variable called severity. And so the higher the number, the more severe the injury is. Well, if that's the case, I really should accommodate for this, right? So this is kind of a covariate. Now I'm going to remember this graph that I made in the first one where I was just comparing those 3 treatments. Well, if I'm going to switch this now and make a different graph. Time to recover again on the Y. And I did that same thing where I've got the open circles for all the censoring. And now I'm going to put severity on the X-axis. Turn off the smoother. And so as we would guess that the more severe the injury, the longer it's going to take. That's going to be more obvious when I incorporate the treatment. And so if I bring treatment in here, And so now I'm going to fit the regression line. And I know that's not exactly correct because the censoring would make those slopes be bigger than they are. But I just want to do this for the visual, just kind of visually see that. And so now if I look at this, I'm like, aha, there's definitely a relationship between severity and time to recover. And now I'm going to rerun the analysis comparing the treatments by taking into account this covariate. And so I'm going to do that proportional hazards model, time to recover, got to identify the censoring, and I'm going to put treatment and severity. And in fact, what I'm actually going to do is I'm going to select this factorial to degree 2. And what it's going to do is it's going to fit a Cox proportional hazard model where it's going to have an interaction as well. Because I want to see if there's an interaction between the treatment and severity. It didn't look like there is when I looked at this graph, but you know, it's nice to formally test that. And so I'm going to hit run. And one of the things you get when you start fitting sort of these multi-factor models is at the top, I'm going to get a statistical test for each of those terms that I put into this model. And the first one I want to look at is this interaction. And I can see that that interaction does not have a significant p-value. Now with JMP, you don't have to go back to the dialog box here, open this up, and then take out the terms you want to take out of the model. You can do this right from the report. So if I click on the interaction and click remove, it's going to refit the model, but now only a main effects model. Okay. Now I knew treatment was significant. I can kind of see severity was significant, but just, you know, if you need to report the actual test. But what I'm going to do is I'm going to go and do those hazard ratios. Let me close up a bunch of this output because it's going to be a little confusing looking at this all. So in addition to the hazard ratios I got before comparing the 3 treatments, so A to B, A to standard, B to standard, I also now have a hazard ratio done for the numeric continuous variable. And so I'm going to get 2 hazard ratios. One is for the unit change, and that's this one on the top here. And so that's for every 1 unit change in severity. And then this one down here is across the full range. And let me see what the lowest was here. So 2. So 2 is the lowest severity and 10 is the highest. And so this is the hazard ratio comparing a athlete with the injury at level 2 to the athlete with an injury at level 10. And I'll choose the reciprocal, so it's you can kind of see what's happening. That as I'm moving up in every unit change. Oh, actually, no, it's better. I use this first one. So as I move up in 1 unit of severity, the rate of recovery is 0.6, the rate of recovery of that previous severity level. So you can see as that severity level is going up, that recovery rate is actually that instantaneous recovery rate is going down. And then this one, you can see how large that is, or how large, or I should say small that is, or large the reciprocal is, because that's comparing 2 to 10. Now, down the bottom, let's look at the p-values for this again, comparing the treatments. So not a significant difference between A and B, but now look here. We have a significant difference between A and the standard and B and the standard. So again, we can, whatever we want to put in the numerator and whatever we want to put in the denominator. So if we were doing it this way, we could say that the recovery rate for A is about 15 times greater than that of the standard. And for B, it's about 9.7 times that of the standard. And again, here are the confidence intervals, so I can incorporate the uncertainty there. So you can see how wide those are. So what has happened is that now that we've incorporated this covariate severity, not only are we seeing the difference between A and the standard we did in the first analysis, but now we're seeing a difference between B and the standard, but we're not seeing any difference between A and B. So this covariate has helped clean up the variation, making it easier to see. Now, another way that I could fit a model to these data is I can use this, this platform called Fit Parametric Survival. And so now this is going to be more parametric because I'm going to assume a distribution I'm going to work with. And so I'm going to do time to recover, censoring, and I'm gonna do the same thing as I did before, where I'm gonna put treatment and severity up to the interaction in here. I know it's not going to be significant, but I'm going to do it anyway, just so you can see the output. And I'm assuming a Weibull distribution. So you can almost think of it as I'm modeling this data with a Weibull distribution, but the location parameter is basically this linear function of this model I'm building. So it's like it's almost as if there's a linear regression component sitting up inside of an exponent. So when I hit run, so very similar output where I've got this effect summary table. For those of you who use JMP a lot, you might use this fit model platform a lot. Well, this fit model platform is our most general linear model platform. Inside of here is where I can do parametric survival and proportional hazards as well. So basically, this is the same as doing it that way, but because it's so common in survival analysis, we also just wanted to put the way to access it here as well. But some of you might be doing this and you're going to the fit model platform. It's the exact same. It's just a different way to launch it. So I'm going to pull out the interaction term. But what I like about when you fit these kinds of models is now let's open up some of my profilers here. And so I'm going to open up. Okay, and now I'm not going to change it, but I understand those aren't failures; those are recoveries. But now that I fit this linear model, so to speak, I can now choose conditions like whether it's the treatment, the level of severity, or the number of weeks, and then I have an estimate of the proportion of people that would recover from that injury by that time, along with the confidence interval. Or as I've shared the other way around, is you can pick a treatment, you can pick a severity, and then you can pick a proportion of people that have recovered. So I'll just pick 75%. So I've got an estimate of at what time, what number of weeks with a confidence interval do I expect, let me just change this to an even number here, 7. Do I expect athletes to recover if they have a injury at a severity of 7 and they're receiving treatment A? How long will it take for 75% to recover, and have an estimate of that? Now, some of you probably don't know this, but I'm going to kind of do this little routine. If you're comparing different things, well, so here's the thing. You're going to get a report from JMP, and there's going to be a set of graphs and tables, and you've got your red triangle to choose more. But sometimes you want to create a graph different than what's here. Like maybe you want to create a very specific style of graph. So let's say for the purpose, I want to make a couple comparisons. And so what I'm going to do is I'm going to pick, let's see, I'm going to pick one of these settings here. I'm going to pick, let's say, severity for treatment A, 10 weeks. Okay, so I'm gonna pick something a little bit bigger just so the number's not so close to 0. So, okay, now I picked one that's now close to 1. Hold on. Let me find a nice little balance. We'll find a little balance there. Okay. So when you have a setting with the profiler, you can save that. And so I'm going to go under the red triangle, factor settings, remember settings. You give it a name and hit OK. And then what's basically going to happen here is I'm going to start building a table. So I'm going to try different things. So let's say I'm going to try, let's say now I'm going to do the standard. Same thing, factor settings, remember settings, give it a name, hit OK. So you're seeing this table get built down here. Now I'm going to do a 6 weeks, just saving these. And then I'm going to do standard 6 weeks. And so I just have these 4 that I've saved. Now, anytime there's a table in JMP in a report, if you right click on it, you have the ability to send that table into a JMP data table. And so if I right click on it and say make into data table, now I have this graph right here, which has those 4 estimates I've made. Now what I'm going to do is I'm going to turn severity into a ordinal variable just because the graph I want to make, I know it needs to be that way. So I'm going to bring up the graph builder. And again, I know this is recovery probability. I'm not going to change it. So I'm going to put that there. I'm going to put treatment on the x-axis and severity also on the x-axis and inside of it. And I'm going to make a bar chart. All right. So now I'm basically just showing the, I can label it if I want. So I'm just showing, I can even change that let me change the format just to be a little bit better here. I'll put it to, okay. Oops. Okay. All right. Now, so these are the point estimates of those the amount of athletes that would be recovered under those 2 treatments at those 2 severity levels. But inside of this data table are the confidence intervals. And a lot of people don't know this. You can do this in JMP. But if you have those confidence intervals, the lower and upper bound in your data table, if you just grab those and bring them over here and drop them in the interval role, now what's going to happen, let me bring this down, is so now I've got these blue lines representing the confidence intervals. And I can do things like I can change the color of these things if I want. Okay, I'm not saying that's the color I'd pick, but just showing you can do that. So the reason why I'm pointing this out is I get this question a lot. People say, oh, how inside of this report I want to create kind of a graph that's not being created. Well, if you've got the data values and the numbers, however you get them, whether it's a table JMP prints out automatically, or in the case I just showed, I made the data table. Well, bring that data into a JMP data table file, and then I can open up Graph Builder, and I have all the capabilities of Graph Builder there. Okay, I'm not seeing any questions popping up, Ross. So I guess you're answering them as we're going along the way.
Yep, we're looking good, Kevin.
Okay, perfect. Now we're coming to the end, and now I had this other data set. I had a feeling I wasn't going to be able to get to it, but I just want to open it up and maybe give you guys a data set to kind of play around with, or maybe use for a class demonstration or a class assignment. This data set is something that has a lot of variables, and so I've got 2 different time to event variables in here. So this is a collection of breast cancer patients, and so the one variable I have is the time to for a reoccurrence. And when you look at this data, you'll see actually most of it is censored. So so there's 1,300 patients in this data set, and 771 of them at the point of having studied them, or at the point of doing the analysis, the reoccurrence hasn't happened yet. So, for example, that first person Well, there's been 7 years for there a chance to be a recurrence, and it just hasn't happened yet. But this second one, well, at 12.6 years, there was a recurrence. There's third one at 0.2 years, there is a reoccurrence. And then there's another set of time to event data, and that's actually their survival, right? So whether they are still living or deceased or not. And then there's also information if they actually died of cancer or they died of something else, because obviously that's important as well. And so there's a bunch of variables in here, like their age, of which they develop breast cancer. There is this index called the Nottingham Prognostic Index, which is basically this composite score that's made up of things like the size of the tumor, how aggressive it is, like how many lymph nodes it may have spread to. But basically, the higher the number, the worse the prognosis is. And I think it's made up of like 4 or 5 different variables. But again, the higher the number, that it's just more severe. Some conditions on the breast cancer. And so there's ER status, HER2 status, or PR status, positive and negative. And so it just basically has to do with the type of cancer in terms of does it have estrogen receptors on it or not? And then it kind of actually affects like what the treatment is. It doesn't necessarily mean if it's positive, it's a worse scenario than the others. It just basically just means like what can kind of feed this cancer, and so it kind of dictates the treatment. So there's a bunch of variables that are kind of about the condition of the cancer. And then there is the treatment, and there's 3 different variables. And so there is the type of surgery. Did the patient choose to do a full mastectomy or just a lumpectomy? And then was the chemo involved, or was hormone therapy involved? And actually, sort of whether you get chemo and or hormone therapy is often based upon these conditions. Like if something's has estrogen receptors, then hormone therapy is typically recommended. Now, this file I have here actually has a bunch of analyses I've done saved already. And again, I knew I wasn't going to have time to do them, but I just want to kind of have this at the ready. But one of the things I wanted to do here is, before you jump into analyses, I always think it's great to plot the data. And I wanted to kind of point this out. So I did that same thing where I have everything censored, has an open circle. And so if I'm going to do, let me see the graph I want to make. I'm going to make this one right here. I'm going to slide this aside. You'll see what happens in a moment. So graph builder. Again, I understand most of this data is censored, but I like to look at stuff like this anyway. I'm going to I'll put the age diagnosis there. But I'm actually going to launch the column switcher, because what I want to do is I want to be able to plot either of those numeric variables, the Nottingham index or age of diagnoses. And then I'm going to launch the local data filter, and I am basically going to put in here, make this a little bigger. I'm going to put in here those different conditions. And so now, if you haven't done this before, this is what allows me to change this graph to just a specific set of patients. So for example, if I was like, okay, what if it's HER2 positive, ER positive, PR negative, they got chemo, they got hormone, and they just did a lumpectomy. Okay. Notice just one person in there. Okay. And so the reason why I always graph data is I like to see where is the data. And so another graph I did, it's kind of the same thing, except I decided to see a different, basically this is kind of the same view. Now I just have a little mini scatter plot for every single category. So before I build models, I almost always start with graphing the data. Again, I understand the censoring. I get that that's going on, But the thing that I'm mostly doing this for is so you can start to see all of these categories. Like, look how little data there is here. I mean, there's no data in there. There's one data point there, and it's even censored, one data point here. And so I always like to plot the data because this can sometimes dictate, well, how do I build a model? Because if you start trying to use a model to capture everything, it's almost like it's extrapolating. You can think of it that way. Like this model, I get you might have interaction terms and all this, but the model is trying to account for everything. And it starts to break down a little bit when you kind of have situations like this with a lot of missing data. And so for this one, this is where you might want to filter the data. And again, I brought this example up. It's really for you to go through on your own, but I just want to show you one thing to do is I can launch this thing called the global data filter. And what I can do is I'm actually just going to throw in all the variables here. So I'm going to put age all the way down to the treatment. And now what I have here is some controls. And I'm going to choose show and include. So if I wanted to filter the data and say, look, I only want to do analyses on patients that are HER2 positive, have HER2 positive breast cancer, then I can just click on that and notice it's filtered all the data. So when I go to run an analysis, whatever it is, whether it's a graph or a model, it's only going to do so on data I selected, right? So I could say, what about everybody that's had chemo and hormone therapy, and they had a mastectomy, and they are at least 35 years of age. And so this is a thing I wanted to point out because a lot of people don't know this in JMP is you don't need to have a separate data table for each subset of data you want to run an analysis on or create a graph on. You can just create this data filter and then filter the data any way you want and just work off of one data table the whole time. So I have in here for this file that you'll have in a day or two is a bunch of graphs, and I go and I run a bunch of parametric survival models, starting off with a full model with all the main effects and interaction, and reducing them down based upon significance level. So I'll leave it for you guys to play with that data on your own.